Okay, we're going to go over assignment 21. So the first question, it says, is age distribution of students and their household family members typical of the age distribution of all U.S. residents? All right, so we need to decide if it's a goodness of fit, a homogeneity, or independence chi-squared test. All right, well, in this case, if I'm trying to decide, for example, if it is goodness of fit, we typically want to have some kind of model or rule or theory to follow. And in this case, they actually give us the rule. They give us the model. They say that 22%, 28%, 50% lie within these age ranges. So that right there is what's going to make it a goodness of fit test. There's a rule or a model to follow, and that's this over here. Now, remember, when you write your hypotheses for a chi-squared test, you're not going to write actual like P equals P equals P equals like you would on any other test. You're going to write a statement. And so if I look up here, it says, is the age distribution of students and their household family members typical of the age distribution of all U.S. residents? So our null, because we think of it as an equal sign, is going to be that the age distribution of students and their households is the same. Remember, equal is the same as all U.S. residents. The alternative would then be that it is different, okay, that it is not the same. All right, so now we need to calculate the expected counts. Now, this is where your rules come into play, 0.22, 0.28, 0.5. We're going to take each of these and multiply it by the total number of participants, which in this case was 200. That's your sample size. So 0.22 times 200, I got 44. 0.28 times 200, I got 56. 0.5 times 200, I got 100. And if you add these up, it should equal 200. These two things should equal the same thing right here, which they do. All right, now we're going to test our conditions. And if I look over here at the notes, our conditions are random, independence, the data must be counted, and your expected counts must be at least 10. You do not, remember, have to test for approximately normal because the data is always skewed right. Always skewed right. So in this case, we have to assume that the students and their households were randomly chosen. They represent a random sample. The number of households members of one family should be independent of the next. And then remember, our sample size is 200. That is clearly less than 10% of all U.S. residents. This data is given in counts. They counted the number of people in each category. And look at our expected counts, 44, 56, 100. Each of those are at least 10. Now, degrees of freedom. Let's talk about degrees of freedom. When you have a goodness of fit test, it always the cells minus 1 or the categories minus 1. Well, in this case, there were 1, 2, 3 categories. Do not count the total, 3 categories. So I'm going to do 3 minus 1. All right, so that's where you get 2. Now, if you notice now, I have my list of observed data. This is what actually happened. This is what I would have expected to happen. So I'm going to come over here to my calculator, and you see I put the observed in this list. I put the expected. This is what I would have thought would have happened. All right, now this is how you run a chi-squared goodness of fit test. You do control, and I'm going to go add a calculator. Then I'm going to go to menu, statistics, and notice down here it says stat test. And here there's 2 different chi-squared, GOF, goodness of fit, and two-way. We'll use that for both homogeneity and independence. So I'm going to hit GOF. My observed list was the household. The other one was the class. And then my degrees of freedom, if you remember, was 2. And so I'm going to hit OK. And notice I get my chi-squared statistic. This is your test statistic and your p-value. Now, if I go back over here, I still have to show some work. Now, I told you in the notes that if you have a bunch of things, you don't have to write every step. You got to write this is how you do a chi-squared statistic. You still got to show the first and last. First and last, right here. Observed minus expected squared over expected. So, now since there are only 3 of them, I went ahead and wrote all 3 of them. So you do observed minus expected squared over expected. Well, where did I get that? Observed was 51, 44 was expected. So 51 minus 44 squared over 44. Plus, then do the same thing for the next one, 45 and 56. So 45 minus 56 squared over 56, and then find the last one, 104 and 100. So 104 minus 100 squared over 100, and that's 3.43, which is, again, I already had this answer. I just had to show the work on the other page. All right, now we have to show the work for the p-value. We already know the p-value is 0.1796. We just need to show it now. So the work is just chi-squared CDF, lower bound, upper bound, degrees of freedom. We already said the degrees of freedom was 2. Now I put 99 here. You can just put infinity. And then our lower bound is always our chi-squared statistic, and then we just write it. We don't actually have to type this into our calculator. We already did. We know what it is from this right here. It's 0.179, whatever I just said it was, okay? So now, it says define the p-value. Now, that's what I put over here. This is when we assume the null is true. And remember, the null was that the age distribution of students in their households is the same. So if we assume that the age distribution of students in their households is the same as U.S. residents, then the likelihood of getting observed statistic at least as extreme as our, in this case, it's the chi-squared statistic, 3.43, is our p-value. Now, what about our conclusion? Well, two sentences. Because our p-value, 0.1796, is greater than 0.01, that's what we had right here, we retain. Therefore, the evidence does not suggest. Now, what does it not suggest? It doesn't suggest the alternative, a difference. Okay? So it does not suggest that the age distribution of students in their households differs from all U.S. residents. And because we retained, I could have made a type 2 error, because it also said describe the type of error you could have made. We could have made a type 2 error. Now look, when you retain, there's no reason to find residuals, so I don't have to worry about these steps down here. All right, now number 2. Now this one actually says the word differences. And notice I have a two-way table. That's different from the first question. The first question did not have a two-way table. This has a two-way table, and it says differences. Now, if you have a two-way table, a two-way or contingency table, and you see words like same, difference, change, that's an indicator that it's going to be a homogeneity test. So this would be a homogeneity test because we have a two-way table and we're looking for differences. Okay? And we're talking about the drinks. We're talking about the students and faculty. Are there differences in the drinks that students and faculties like? So when I write my hypotheses, remember, we're writing statements. The null is an equal sign. We got to say the same. So we'd say that the distribution of drinks is the same for students and faculty. Our alternative would then be that the distribution of drinks is not the same, or as we said up here, different. Now we do need to find our expected counts. Okay? Now the expected counts are done a little bit differently on these right here. Now here's what they are, but let's talk about how to find them. Now what you do is you take the total number of students, which are 75, and you're going to multiply it by each ratio. So like 47 over 81, 26 over 81, 78 over 81, 38 over 81. Okay? So what I'm going to do is I'm going to show you how I calculated this 19.47 number. Okay? So I'll go over here, and I will open up a calculator, and I'm going to do the total, which was 75, times, and then I'm going to multiply it by that ratio, which was 47 over 181. And when I hit enter, I get 19.475, which you can see, 19.475. So again, I took 75 and multiplied it by 47 over 181. Now let's talk about this 10.73, and then it's kind of the same for each. So I'm just going to go up, and I'm going to copy this. And I'm going to change 47 to 26, and I get 10.7735, which is right here. 10.773 is what I put. And I could continue to do that all the way down for this one and this one. Now let's do one for the faculty. This time I'm going to do 106 times 47 over 81, and that's how I get this 27.5 number. 106 times 47 over 181. So I'm going to go up, and I'm going to copy this original one. And I'm going to change this to 106. And notice I get 27.525 basically. And that's what I had right here, 27.525. So I get each of these different expected counts. Now what about the degrees of freedom? The degrees of freedom for these is going to be rows minus 1s times columns minus 1. So in this case, don't forget, ignore the totals. Those don't actually count. So you have 1, 2, 3, 4 rows and 2 columns. So 4 minus 1 times 2 minus 1, which is 3 times 1, or 3. All right, now, when you do your conditions for homogeneity, these are a little bit different. Okay, you do not have to do the 10% rule, all right? And you also don't have to do random, because with the homogeneity rule, you're using the entire population. You only have to do independents, counted, and expected. So you never have to do the 10% rule, nor do you ever have to do random, because you're using the entire population. You're using everyone. So in this case, we would say that the drink preference, because that's what we're talking about, drinks, of one student or faculty member is independent of the next. The data is giving counts. They clearly counted this data. And the expected counts, if I look at them, every one of these are at least 5. So the conditions are met. All right. Now we're going to talk about how to do the significance test. Now this one you're going to have to create a matrix. So what I do is I hit menu, and right here it says matrix, and then I'm going to create a new one. And I'm just going to create a new matrix. So the rows, if I go back over here, the rows go across. So there were 4 rows, and then there were 2 columns. So 1, 2, 3, 4 rows, and then 1, 2 columns. Remember, do not include the totals. Okay, so I'm going to make it 4 and 2, and then I'm going to hit OK. And now I'm just going to enter the original data. I'm going to enter this data up here. And so that's going to be 15, 32. I just hit tab to go from one to the next. 8, 18, 38, 40, 14, and 16. So I'll just check it really quick to make sure it's correct, and it is. And so I'm going to hit enter, and now I want to store this. So I'm going to just do control store, and I'm going to call it M for matrix, and I'm going to hit OK. So now let's go to where we run the test. So I'm going to do menu, statistics, test, and now we're going to do the two-way table. We do this for both homogeneity and independence. And now notice I'm picking a matrix, and it's the observed matrix, which I just called M. And when I do this, I get my chi-squared statistic and my p-value. And if you go back over here, you'll see that that's what I had for my chi-squared statistic and what I had for my p-value, but you do have to show your work. So in this case, I'm going to show the first step. Now, if you look, my observed was 15, my expected was 19.75. So observed minus expected squared over expected plus ... Now we're going to do the last one, which was 16 and 17.5769, which I did. 16 minus 17.569 squared over 17.569. And then I'm just going to put the answer right here, 5 point whatever I had. Okay, I'm going to put that right there. Now the p-value, we already know it should be 0.1705, but I do have to show the chi-squared work. So lower bound is just going to be my statistic. Upper bound, I just suggest use infinity, but if you have the 84, it's 99 or whatever. And then remember, our degrees of freedom was 3, and then I'm just going to write that number on our calculator. So how would I define the p-value? If we assume the null, remember the null was here, the distribution of drinks is the same. So if we assume that the distribution of drinks is the same for students and faculty, then the likelihood of getting an observed statistic at least as extreme as right here, our chi-squared, is our p-value. Now what about our conclusion and our type of error? Well, again, it's too big. 0.1705 is bigger than 0.01. So because 0.705 is greater than 0.01, we're going to retain the null, so the evidence does not suggest the alternative, that there's a difference. It does not suggest that the drink distribution differs for faculty and student member. Now, anytime you retain, there's a chance of a type 2 error. Once again, because I retained, there was no reason to find the residuals. We're only going to find residuals if we have some type of issue where we have to reject. All right, now we're on question 3. Now notice again I have a two-way table. When I see a two-way table, I should be thinking either homogeneity or independence. And in this case, I see the word association. Well, if we have a two-way table and I see words like independence, association, or relationship, that's a sign that it is an independence test. So it's an independence, chi-squared independence, because we have a two-way table and we're looking for an association. Now, when we write our hypotheses, since it's an independence test, we like to use words like independent and not independent. Well, we learned way back in Unit 1 that if independent is what it's always independent for the null. Always independent for the null. That means no association. So we're talking about income level and political party. So income level and political party are independent. Are independent, again, means that there's no association. The alternative would be income level and political party are not independent, which means that there is some type of an association. Now, when we find our expected counts, we do it exactly like we did before. We take, just like with homogeneity, we take our total and we multiply it by the ratio, which in this case would be 84 times 58 over 2 over 2. So let me show you. So I'm going to create a calculator, and I'm going to do 84 times, all right, and then I'm going to do 58 over 2 over 2. Oops. And you get 24.119, which is what I had right here, 24.119. If I want to find this 30 number, I would do 84 times 74 over 2 over 2. So I'm just going to go up here, and I'm going to change this. Oops, well, I didn't mean to do that. Let's retype that again. So we're going to do 84 times, and I'm going to change it this time to 74 over 202. And you get 30.777, or 30.772, right there. Now, what if I want to do this 22.3? Well, this time I do 78 times 58 over 2 over 2. 78. So I'm going to come back up here, and then I'm going to hit enter, and I'm going to change it to, instead of 74, I want it to be 58. And instead of 84, this time I want it to be 78. And notice I get 22.396, which is what I got right here, 22.396. And I would just repeat that process for the rest of them. Now, your degrees of freedom, remember, is rows minus 1s times columns minus 1. Okay? Well, don't count the total. So this has 1, 2, 3 rows, 1, 2, 3 columns. So 3 minus 1 times 3 minus 1, which is 4. Now, what about your conditions? Your conditions, you're going to go back to what you had for goodness of fit. You have to do random again, and you have to do the 10% rule again. Okay? So we assume the sample was randomly chosen. One person's income and political party is independent of the next. Remember, the sample was 202. That's less than 10% of the population, all people. Clearly, the data was given in counts. We counted the number of Republicans and Democrats and low and middle and high income people. And all the expected counts. Look at them all. They're all at least 5. All right. So what I want to do now is I want to do the goodness of fit test. I'm sorry. Yeah. Not the goodness of fit, the independence test. So to do that, I need to create a matrix again. So I'm going to go menu. Number, nope, that's not right. Matrix is down here. Number 7 is matrix, create matrix. And if I look at this example, remember, it's a 3 by 3. So I'm going to make it 3, 3, hit OK. And then I have to just type in my expected counts, which were 30, 16, 12, 28, 24, 22, and then 26, 38, and 6. All right, let me just check to make sure 30, 16, 12, 28, 24, 22, 26, 38, 6. All right, looks good. So I'm going to store this. I'm going to do control vars. I'm going to call it M again. And so now M is this matrix. So let's run, remember, homogeneity and independence. We're going to go to statistics, stat test, and because it requires a two-way table, we're going to go here. You pick your matrix, which again was M, and there's your value, 17.192, and then a pretty low p-value. So if I come back over here, you can see there was 17.192, and there's my pretty low p-value. But again, you have to show the work. You have to show first and last step. So the equation is, here's the observed 30, here's the expected. It's observed minus expected squared over expected plus dot, dot, dot. Now do the last one. Observed is 6. Expected is 13.8661 squared over 13.861. And there was your 17.1892, which is right here. And then we already know the p-value is 0.00177 from this right here. All right. So remember, lower bound is always the statistic. Because remember, these are always skewed right. So I just suggest you use infinity unless you have a TI-84, then use 99 or 999. Your degrees of freedom was 4, and that's what you got. So if we assume that the income level and political party are independent, because remember, you got to assume the null, okay, and we're defining the p-value, then the likelihood of getting an observed statistic at least extreme is our chi-squared, 17.192, is 0.00177. Our conclusion at a 0.1 and our type of error, well, because this time our p-value is less than 0.01, we'll reject, which means that the evidence does suggest the alternative, which is that they're not independent, or you could say that there is an association, okay? Therefore, the evidence does suggest that income level and political party are not independent, or you could say that there is an association. Now, since we rejected, that means there's a chance of a type 1 error. In fact, it's our alpha level of 0.01. Now, this time we rejected, which means that we have to find our residuals to see why there may have been these differences. So our equation for residual, is right here. This time they use the letter C instead of E because it's a different type, but it's observed minus expected over the square root of expected. So I'll do a couple of these just to kind of show you, like how I got this 1.1979. So my observed was 30. My expected was 24.119. So if I go over here.
Teachers and students, please pardon this interruption for an announcement. Students that ride Irmo Bus 57 will ride Bus 44 today. Again, students that ride Irmo Bus 57 will ride Bus 44. All students are dismissed. Have a great afternoon.
All right, sorry about that distraction. All right, so we're going to do observed 30 minus our expected, which is 24.119, divided by the square root of the expected, which was 24.119. Hit enter, and you get 1.197, which was what I had right here, 1.197. I'll do one more. I'll do the Republican one right here, okay, just to kind of show you how to do this. So I'm going to go up here, and I'm going to just get the same thing in, but I'm going to change the number. So the Republican was 16. The expected was 22.396, and then I'm going to divide it by 22.396, and I get negative 1.35, and you can see negative 1.35. So you calculate all these the same way, and so then you're just kind of looking for positives that are negatives. Like positives mean that there were more than you expected, negatives mean there were fewer. So if I look at the Democrats, there were more low-income Democrats than I would have expected. If I look at Republicans, there were more high-income Republicans than I would have expected. Independents, there's more middle income than I would have expected. Also, look at this negative. It's the lowest of all, and there were also a lot fewer high income. So you just kind of comment on a few of those things, and that kind of gives you a feel for how you will interpret our residuals. All right, now we're on number 4. And here they're talking about rolling a die, and they roll it 60 times. So if you roll a fair die, you can get 1 through 6. This is what they actually got, and this was what was observed. 11 ones, 7 twos, 9 threes, 15 fours, 12 fives, 6 sixes. But then it says, how many times would you expected it to be? Well, think about this. If it's a fair die, 1 out of 6 is what you would expect at each side. So if there's 60 total rolls, 60 times 1 6 would be 10. So we would have expected each one to be 10. Each one should be 10 if it's fair. Okay? All right, now, because we used a rule right here, and remember, if it's goodness of fit, you're not going to have a two-way table, and you're looking for a model, a rule, or a theory right here. So there is no two-way table here, and we just used a rule. We multiplied by 1/6. All right, so that means it's going to be a goodness of fit test because there's a rule, the 1/6. So state your hypotheses. Well, remember, the null is always an equal sign, so the distribution is the same as a fair die. Remember, we're looking at a fair die up here, somewhere up here. All right, the distribution is the same. So the alternative would be the distribution is not the same. It's different. So that would make it an unfair die, like it talks about here. All right. Now, your degrees of freedom, when you have a goodness of fit test, is the number of categories. We have 6 minus 1. So 6 minus 1 is 5. And then we're actually going to find our chi-squared statistic and our p-value. Now, I have already typed these in over here. These are the numbers. So I'm going to go to a blank calculator screen. I'm going to go to menu. I'm going to go to statistics, stats, and this time I'm going to pick the Goff test. My L1 is the observed. My L2 is the expected. And again, my degrees of freedom was 5. Hit OK, and I get 5.6 and 0.3471. And if you come back over here, that's what I had, 5.6, 0.3471. You do have to show the work. So the work, I show the first step and the last step. So the first step was 11 and 10. So 11 minus 10 squared over 10 plus dot, dot, dot. The last step was 6 was observed, 10 was expected. So 6 minus 10 squared over 10, and you get 5.6. We already found that. Don't forget, when you do your p-value, which we already found right here, here's my p-value. All right. You do chi-squared CDF. The lower bound is always going to be the statistics. Remember, it's always skewed right. My upper bound, I would just suggest you put infinity, and then our degrees of freedom was 5.347. So now your conclusion, because this p-value is greater than 0.05, we will retain the null. So the evidence does suggest the alternative, which is that it's different, which basically means it's unfair. Something different from a fair die, meaning that it is an unfair die. Okay, so you could just write unfair die. All right, number 5. So here it says, explain why a chi-squared goodness of fit test is not appropriate. Now, anytime ever that something is not appropriate, it means a condition is not met. Okay? Well, if you recall, for all of these, one of the conditions is that you must have expected counts. So you must be dealing with counting data. I'm sorry, the counted data condition. You must have counts, categorical. Well, in this case, grams. Notice it says 112 grams, 193 grams, 207 grams. That is a measurement. That means that this is quantitative. It's a measurement. Remember, grams, a measurement, is quantitative. We want counts. So the condition is not met. All right, now we're on question 6. Now, number 6, it talks about this model or this ratio, 9-3-3-1, for the genetic theory, the body types of these fruit flies. So 9, you have yellow normal, 3 is yellow short, 3 is ebony normal, 1 is ebony short. And so let's suppose you have a total of 100 such fruit flies, and we want to know if it follows this genetic theory model. Now, I gave it 9-3-3-1. Now, if you add those numbers up, 9-3-3-1, you get 16. So if I want to find my rule, it would just be 9 out of 16, 3 out of 16, 3 out of 16, 1 out of 16. The 16 comes from the total. The 9-3-3-1 comes from the ratio. So we would expect 9 out of 16 yellow normal, 3 out of 16 yellow short, 3 out of 16 ebony normal, 1 out of 16 ebony short. Okay? Now let's suppose we're told that these are the observed counts. Right here, 59, 20, 11, 10, which equals 100. Let's suppose we're told that. Okay? Now the expected counts, what I do is I take the total right here and I multiply by 9 out of 16, which is 56.25. Then I take 100 and I multiply by 3 over 16, which is 18.75. Do it again. 100 times 3 out of 16 is 18.75. And finally, 100 times 1 over 16 is 6.25. Okay? These would be my expected counts. So, because this is going to be an example of a goodness of fit test, because we do a goodness of fit test whenever we have a rule, model, or a theory, and in this example we had the genetic theory. So we're going to assume, remember the null is an equal sign, we assume the distribution of body wings is the same as the genetic theory. The alternative would be the distribution is not the same or it differs from the genetic theory. Now I'm going to come over here to the calculator, and I've put this right here. You can see observed 1, expected 1, and that's what we had for this. So I'm going to go to a new calculator. I'm going to run the test. And this is goodness of fit, and so I'm going to pick observed 1, and then I'm going to pick expected 1. The degrees of freedom, because you had 4 different categories, 4 minus 1 is 3, and you get 5.67 and you get 0.1288, which if you look, is what I had right here. 5.67, 0.1288. Now you do have to show the first step and the last step again, kind of like I did on the previous ones. You also have to do lower bound, which will always be the chi-squared statistics. Remember, this is always skewed right. I would just put infinity on yours, and then the degrees of freedom was 3, and you get this 0.1288. So in this example, because the p-value is greater than 0.05, we would retain. So the evidence does not suggest the alternative. It does not suggest that the body wing type differs from the genetic theory. Now, let's suppose this time you double everything. So instead of it being like 59, 20, 11, 10, you double it and make it 118, 40, 42, 20, which is what I have right here. So this time you have a total of 200 flies instead of 100. So I'm going to take these same 4 fractions, but this time multiply it by 200, and I get this values right here. Okay? Get those. So now, I'm going to go back in, and you'll see that I've entered this data into observed 2 and expected 2. Okay? All right, so this time, I'm going to do a goodness of fit test, but I'm going to do it for the second list. So I'm going to do goodness of fit. So this time it's going to be observed 2, and it's going to be expected 2. My degrees of freedom, remember there were 4 cells or categories, minus 1, which is 3. And you get 11.34 and 0.01. So you can see 11.34, 0.01. So as soon as I cranked up the sample size and I changed it from 100 to 200, it actually changed my results. This is what it was originally. This is what the p-value is now. Notice again, I showed the work for the first step and the last step, and I still had to show my chi-squared statistic work, okay, chi-squared CDF work, all right? So this time my conclusion, because 0.001 is less than 0.05, we reject. Therefore, the evidence does suggest the alternative. So it does suggest that the body wing type differs from the genetic theory, okay? It is different. So why is there a discrepancy between the two conclusions? Why did I retain here but reject here? Well, what this means is that the more evidence you have, in this case, the more fruit flies you have, all right, the better your data is going to be. So you're going to more likely be to make the right decision to go ahead and, in this case, reject the null. All right, number 7. So here you have a two-way table. All right, if you see this, we have a two-way table. All right, and whenever you have a two-way table, when we're thinking about chi-squared, it's either going to be a independence test or it's going to be a homogeneity test. We kind of look for our key words. Now this one says association. So whenever you have an association, that's going to be an independence test. So this is going to be chi-squared independence test because we have a two-way table and we're looking for an association between the nursing success and epidurals. So now it says our hypotheses. Now remember, our hypothesis always needs to be, if it's an independence test, that the values are independent, so that the two variables are independent. So we're talking about epidural and nursing success. So we're going to say nursing success and epidurals are independent, which implies no association. We learned that way back in chapter 1. Okay? And then our alternative would be that nursing success and epidurals are not independent. Not independent means that there is some type of association that exists. All right, number 8. So number 8, we are looking at a journal magazine, and they're looking at how they're comparing 3 different eras of publication, the 70s, the 80s, and the early 2000s, and then whether or not these articles included statistics or not. So again, you have a two-way table. When you have a two-way table, this is either going to be a homogeneity or it's going to be an independence test. Now, if you read right here, it says researchers want to know if there's been a change. When you see words like change, same, difference, that tells you it's going to be homogeneity. So our null is always going to be some kind of equal sign. So in this case, it's going to be the same. Equal means same. So the distribution of statistics used is the same for the 3 years of publication. The alternative would be that the distribution is not the same or has changed. Remember, it's change up here. Has changed for the 3 years of publication. Now, your degrees of freedom. Your degrees of freedom, remember, when you have a two-way table, is rows minus 1 times columns minus 1. Do not include the total. So this has 2 rows and 3 columns. So 2 minus 1 times 3 minus 1, which is just 2. Now here, it says only find the expected count for 89, 1989, and no stats. So that's this area right here. So no stats, 89. So the observed count was 14. Okay, no stat 14. They want to find the expected counts. So remember, you take your total, which is 115, and multiply it by the marginal distribution of 144 over 178, which I did. 115 times 144 over 758, and you get 21.847. So this is the expected count only for this cell, none of the other ones, just that one. Then it says to find the chi-squared statistic, but only for this. Okay, so again, for this area right here, we only want to find the chi-squared statistic, none of the other ones. Not the total, just this one. So the equation, remember, is observed minus expected squared over expected. Well, the observed was 14. So that's where the 14 comes from. The expected is right here. So observed minus expected squared over expected, and you get 2.82. This would be the chi-squared statistic for only this area. Now, if I wanted to find it for the whole thing, I would have to find all 6 of these here, 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 and add them together, which I went ahead and did for you, and I got 25.28. Then it says to find the p-value. Now, this is a little different because we could go in and type all this in, but if they already give me the chi-squared statistic, I can easily find the p-value on my calculator using chi-squared CDF. So that's what I'm going to do. I'm going to go in here, and I'm going to go menu, statistic, distribution, and here it is right here, number 8, chi-squared CDF. And so my lower bound is going to be that number they gave me, 25.28, because remember, it is always skewed right. So the upper bound, I'm going to put infinity, and then my degrees of freedom was 2. And notice you get this small number, 0.000003, or you could see like how I put over here. I actually was able to put 0.24, but you could put 3.0 times 10 to the negative 6. That's basically the p-value. All right, so our conclusion, because the p-value is less than 0.05, we would reject the null, which means the evidence does suggest the alternative, which is that there was some type of change. The statistics was changed over the 3 years of publication, okay? It does suggest that the distribution statistics used was changed over those 3 years of publication. All right, now anytime ever that you reject, it's a good idea to create the residuals. So I tell you to calculate the residuals only for 89 and no stats, which is the same area right in here. So the question is, how did we get this negative 1.68? Well, the rule for a residual is observed minus expected over the square root of expected. Well, remember, observed was 14. Expected was right here. So observed minus expected over the square root of expected, and this is what you got. Notice that rounds to this. Now, what does that mean? The residual suggests that in the 70s, notice how you have high big numbers. There was a lot more no stat articles in the 70s, and then as you get in the 2000s, there were fewer than we would have expected that had no stats. On the flip side, this negative means that there were fewer cases of stats in the 70s. This positive means there were more cases of stats in the 2000s. So the trend seems to say the closer we get to like modern day, you have more stats than the further back you go. Okay? That's what it seems to suggest. All right, next one. This is another two-way table. Number 9. You have officers, and then you have male. Now notice this one doesn't do like totals. It just gives you the different ranks of officers and then their gender. All right? So first thing it says is, what type of test is it? Well, if you have a two-way table, it's either homogeneity or independence. This is talking about difference. If it ever says same difference or change, you should be thinking homogeneity because it's talking about difference. So your hypotheses, the null, remember, the null is always the same, so it would be no difference. So the distribution of ranks is the same based on male and females or based on gender. The alternative would be the distribution of ranks is not the same, or that it's different among the ranks, the male and female gender. Now remember, when you do conditions for homogeneity, you do not have to do 10%. You also do not have to do random because you're using the entire population. So for independence, the rank of one police officer is independent of the next. The data was given as counts. They counted the number of each. And your expected counts are all at least 5. Now, I didn't calculate them. We could do that in there, but we would see that they actually all are at least 5. So what about your degrees of freedom? Well, if you have a two-way table, you use row minus 1 times columns minus 1, which is what I did. 6 minus 1 times 2 minus 1, which is 5. Now, I go ahead and I tell you the p-value here. I tell you the p-value. That's pretty low. So they say give your conclusion. Well, since the p-value is less than 0.05, we'll reject the null, which means that the evidence does suggest the alternative. It does suggest a difference in the ranks among the genders, okay? Ranks is different among males and females. All right, so then they go in and they calculate all the residuals. And take a look at these residuals. You'll notice that for males, there were fewer of the lower ranks and more of the higher ranks than we would have expected because it's negative here, positive here. Whereas on the female, it was the opposite. There were more positive on the lower ranks, more negative on the higher. So what do the residuals seem to indicate? That males have more higher ranks than we'd expected and fewer lower ranks. On the flip side, females have more lower ranks than expected and fewer higher ranks than we would have expected. Okay? All right, number 10. All right, so now all I want you to do is decide which type of chi-squared test we would use. Notice it's a two-way table. Two-way table tells me right away it is either going to be independence or it's going to be homogeneity. They say the word association, so it has to be independence. The next one, number 11. Notice again you have a two-way table. You have your origin, and then you have the driver, whether they're students or staff. So a two-way table, so it's either homogeneity or it's going to be independence. It says the word differences. That implies that it has to be homogeneity. Number 12. Again, you have a two-way table. All right, a two-way table, and they're asking about an association. So down here on part B, where it says the type of chi-square test, we already know it's going to be independence because they're asking about an association, and you were given a two-way table. So what about part A? Part A says, is this survey, retrospective observational, that's data collected in the past, prospective observational, that's where you get data as it unfolds, or an experiment? Well, you can't randomly assign people to either have prostate or not have prostate cancer, okay? You can't do that. So it can't be an experiment, but it says that the men is one or the other, so either prostate cancer or not. Okay, whether they eat fish or not, that's something that's just that tells you it's observational. And it did say they followed them, or basically for over the course of 30 years, they looked at this data. So if you look at something as it's unfolding, all right, it is going to be a prospective observational study. Okay, prospective observational. Now look at the next one. Here we have another two-way table. Another two-way table. So we know it's going to be homogeneity or independence. Okay. Now in this case, it doesn't actually say anywhere up here like same, difference, change, or anything like that. But clearly they're looking to see if the results from 1991 are the same or different from 2001. So if the years are different, we know it's going to be homogeneity. Homogeneity. Now, this is also an example of a survey. How do I know it's a survey? Because it says a Gallup poll. Whenever you're polling data, it's going to be a survey. All right, number 14. Okay, number 14. Again, we have another two-way table. When you have a two-way table, it's either going to be independence or it's going to be homogeneity. Now, it says we wonder if one professor is easier than the other. Well, easier implies that there's a difference in the two. Difference means that it has to be homogeneity. So they want to see if alpha or beta, which one's easier or more difficult. So if one's easier, that implies they're different. They're not the same. So that would be a homogeneity test. Now, I tell you to find the expected count only for alpha and F, which is right here where you have this 3. Alpha and F. Okay? So the way you would do that, all right, the way you would do that is you would take this total down here, which is 40. You would take your marginal distribution, which I don't see over here, but that's going to be 3 plus 1, which is 4, which I did right here, 3 plus 1, which is 4. And then down here would be the total, which is 40 plus 32, or 72. That would be my marginal distribution, 4 over 72, which I'd multiply this total of 40, and you get 2.2 repeating. Now that's a problem, because remember, your expected counts must be at least 5, and in this example, it's not at least 5. In this example, it's actually less than 5. All right, finally on the last problem. So this right here, this actually shows up on the AP exam every now and then. It's pretty rare, but every now and then. And this is where you're going to use the chi-squared table to make a decision on whether to retain or reject the null. Now, we already know that if the p-value is less than the alpha level, we reject. We know that if the value in our null hypothesis is not inside of our confidence interval, we reject. But now we're going to learn a third way. If the chi-squared statistic is larger than the critical value, now the critical value is what's on the table, you're also going to reject in this case. So if I look right here, all right, I clearly have a two-way table up here, right up here. And if I have a two-way table, I can find degrees of freedom, all right? Because remember, don't worry about the total. So you have 3 rows and you have 2 columns. So the degrees of freedom is 3 minus 1 times 2 minus 1, which is 2. That's my degrees of freedom. That's 2. Now, they're asking about, it's a kind of a weird alpha level, but they want 0.025. So if my degrees of freedom is 2, and my alpha level is 0.025, I'm going to find where they intersect. So there's 2, there's point, and you get 7.378. That is your critical value. That's the value from the table. Well, I tell you the chi-squared statistic is 1.57. So guys, if this 1.57 is bigger than this, we're going to reject it. But in this case, this 1.57 is less than the critical value, so we're actually going to retain it. And if we retain it, the evidence will will not suggest the alternative. So the evidence does not suggest that the distribution of athletes using steroids differs in each of the 3 NCAA divisions.